So we're going to take a last look at a function, and this time we're going to have a function that involves logs. So we know this, we're very familiar with the steps now, hopefully. First step is to figure out the domain and the range, and the domain is that x has to be bigger than or equal to 0 because you can't take the log of a negative number. And that also takes care of the denominator because we can't divide by 0, but as long as x is greater than 0, we're okay. So this is the domain. Now, the second part is the intercepts, and we're going to, there's no y-intercept because x cannot equal 0, and there's a x-intercept when y is 0. So when y is 0, we're solving log x over x, which means we're solving for the numerator. So 0 equals log x, and that means x equals 1. So there is an x-intercept at 1, 0. See, there is no symmetry, and there is no symmetry because the log graph, which looks like this, is not a symmetrical graph, and it's not periodic either. But the next is the horizontal asymptotes and the vertical asymptotes. Let's do the horizontal asymptotes. We're going to take the limit as x goes to infinity, and we only have to do positive infinity because of our domain of log x over x. Now if I plug in x goes to infinity here, I get infinity over infinity, which means it's application indeterminate form, and I can apply L'Hopital's rule. So I'm going to take the derivative of the top, which is 1 over x, divided by the derivative of the bottom, which is 1. And that just means I'm taking the limit as x approaches infinity of 1 over x, which equals 0. So I've got a horizontal asymptote at y equals 0. There's a vertical asymptote at let's see if I can squeeze that in. The vertical asymptote is at x equals 0 because that's where the domain is, the denominator is 0, and I'm just going to take the limit as x approaches 0 from the right because that's all I'm allowed to do given the domain. And if I do that, then if you imagine this plugging in the 0, it's heading towards negative infinity, and x approaches 0. So that means that it's going to approach negative infinity, and that means I know I've got a horizontal asymptote at 0, and the graph is going to head down to 0. Similar to this, but there's other stuff happening besides just that graph. So now I'm going to move on to another slide and take the derivative. So I get y, here's my original function, and I'm going to take the derivative, which is the quotient rule. So the derivative of the top times the bottom minus the top times the derivative of the bottom. My pen's not working quite right. To the bottom squared. Simplifying this cancels to give you 1 minus log x over x squared. So the critical points are where the derivative does not exist, and it doesn't exist at x equals 0, but that's not in the domain. The other critical point is where the derivative is 0, so where y minus log x equals 0, which is when log x equals 1, and that means when x equals e. So when x equals e, I've got a critical point, and when x equals e, y equals log e over e, which is 1 over e. So now I'm going to put this on a number line just to track, and I'm only going to start at 0 because I know the domain starts at 0, and I'm going to track what happens. So I know that x squared is positive throughout, and I know that I'm going to track 1 minus log x, and it makes a switch at the critical point, or not the critical point, yeah, the critical point, which is at e. So when it's bigger than e, it's actually negative, and when it's smaller than e, it's positive. Imagine that if x is very large here, that's going to be a large number, and 1 minus a large number is a negative number, so that's why I know that it's negative on the right side of e. So it knows that the derivative is negative on this side and positive on this side, and it means it's increasing and then decreasing, and here is my max, and it happens at e 1 over e. So the next step is to take the second derivative. So I'm going to rewrite the first derivative, which is 1 minus log x over x squared, and I'm now going to take the second derivative. So derivative of the top, derivative of 1 is 0, derivative of negative log x is negative 1 over x times the bottoms minus the top. Oops, lost my x there. Oh, my pen's not working great there. 1 minus log x times the derivative of the bottom, which is 2x over x to the fourth. So simplifying the numerator, I get negative 1, because x, this will cancel, minus 2x plus 2x log x. So I multiplied this into the bracket and made sure that I have got the negative distributed as well. So that's x to the fourth. So I get negative 3x, collecting like terms, over x to the fourth. I'm going to factor out an x, and I'm end up with 2 log x minus 3. I've rearranged the order there too. X to the fourth. I'm going to cancel this, and I get 2 log x minus 3 over x cubed. So I have a possible critical point when the second derivative is 0 or doesn't exist. Remember, x equals 0 is not in the domain, so all I really need to worry about is where this is 0. So 2 log x equals 3, which means log x equals 3 over 2. And solving for that, I get e to the 3 halves. So that's equal to, that's what x is for the critical point. So if, not critical point, sorry, for where the second derivative is 0. So now I'm going to put that on a number line. Starting at 0, I know that x cubed is positive throughout. I'm not going to put that on there at all. And the 2 log x minus 3 is going to switch at e to the 3 halves. It's going to be positive on this side and negative on this side, which means it's concave down to the left of e to the 3 halves and concave up, and that implies there's an inflection point at e to the 3 halves. And what is the y value equal to when e is e to the 3 halves? I'm going to plug that into my original equation. So there's log x over x. The numerator is 3 halves. The denominator is e to the 3 halves, and I'm just going to pretty that up a bit, and it becomes e to the 2e to the 3 halves. So there's my y coordinate, and in the next video we'll put all the information together.